Hello everyone, our project is signature verification. Signature verification is the task that verifies the authenticity of a question signature. The analysis is currently done by human experts who need to be well-trained, certified, and well-paid. So using machine learning to approach this problem might save costs in hiring these people, training and hiring these people. The data set is consisted of 50, it is prepared by CDAR. We found this online. It has 55 distinct names. Each name has 24 original and 24 forgery attempts, samples. So the images, we believe this data set have some issues, so we process the data set in following steps. To eliminate some potential noise in the data set, the original plan was to convert the input RGB images to binary images. But in this process, we may lose some details in strokes, which could be very important for our training purpose. So instead, we try to use a partial binary conversion, which is to convert everything to 0 pixel value if the original pixel value is below a threshold, but to keep the original pixel value if it's above that threshold. And also, we kind of concerned about so after the training test split, we only have 40 distinct names in our data set. So we were kind of concerned about having not enough like distinct shapes. So the model may overfit to the 40 names. So we kind of cut the images in 2 by 2 pieces. By doing so, we were kind of telling the network to focus on the smaller details in smaller patterns.
The major difference between our model and a typical CNN is the triplet loss function. The diagram on this slide is read from bottom up. As you can see, every data instance consists of 3 images: the anchor, the positive, and the negative. The anchor and the positive are 2 authentic signatures written by the same person, and the negative is a forged signature. Then we pass 3 signatures to a same network separately to obtain 3 output vectors. After that, we compute 2 Euclidean distances between anchor and positive and anchor and negative. We also define a margin in the network, and the network is learning to push negative vectors away. The network is learning to push negative vectors away from positive vectors by the value of margin. The loss function is margin plus positive distance minus negative distance. By minimizing loss, we are pushing negative samples further away.
The neural network is based on VGG16, which is a neural network that is a pre-trained model that's known for picking up details in images. We utilize the advantage of the pre-trained CNN, but modify the fully connected layers to suit the purpose of this project. We keep the first 10 layers fixed, the parameters fixed, and only train the last 3 layers of CNN and the 3 layers of MLP.
Before getting into the result, I want to briefly talk about our baseline model. Very similar to the triplet one, our baseline model only has 2 image inputs and a label. If the label is authentic, we minimize the distance between output vectors, and if the label is forgeries, we maximize their distance. The accuracy of 2 models are summarized on the chart. The overall accuracy of triplet is much higher than the baseline model. The testing result of the baseline model on the CETA dataset is 65%, and the testing result of TripletNet is 95%. Also, both networks on the CETA dataset have very high sensitivity, and almost all forgeries are detected. However, we also tested our dataset on another. We also tested our model on another dataset. On the new dataset, we have the baseline has 60% accuracy, and the triplet has 63% accuracy. And this is when we realized the dataset we used to train our model is not representative to the reality. This sort of makes sense because 40 signatures probably cannot cover everyone's writing habits. Another thing that is suspicious is the model converts very quickly. It means either the dataset is too easy, for example, the forgeries are too obvious, or the model picks up something other than the handwriting itself.
So qualitative results. On the CETA dataset, when given 2 authentic signatures, the model is very good at detecting whether the third one is forgeries or authentic. But when applied to another dataset, the model seems to become less sensitive and predicts more false negatives. The two new concepts we tried in this project both worked well for us. The triplet loss equipped with the triplet loss function achieved high accuracy, and transfer learning reduced our training time. But many things caught us on surprise. The network converged, for example, the network converged very quickly. We have 50K data instances and the batch size is 5, so we should have 10K batches in one epoch. However, we can stabilize at low loss and high accuracy within 400 batches. For improvement, the training data set could be more representative. For example, we lack the the data that represents pens with different thickness, and this is reflected by a lower testing accuracy on when applying this model to a new data set. Thank you all.
That's good. An interesting problem to work on, and tricky in a bunch of ways. And great to see that triplet loss. We've seen that before. It seems to help in this kind of world. First question. Why didn't you want to use the full resolution of the images? Like why? Yeah, I know I got that you went to this partial binary thing, but why not the full resolution?
Do you mean like the RGB images?
Yeah.
Oh, so we tried to eliminate some noise in the dataset. So we noticed that the forgeries data and the authentic data have different background color. So we don't want the model to pick up some misleading factors such as the background colors and the pen colors.
That was going to give it away.
Sorry?
You thought that the background color was going to give away the image.
They can cheat by recognizing the ink color and the background color of the paper.
Maybe some augmentation without. Yeah, I'm trying to think how you deal with that. But that was common across the whole data set.
Yeah. Well, some data sets have that issues. So.
Some of the 40 people.
No, the CEDA data set have that issues, but we have found more than 3 data sets on the data online, and some of them have that issue. Some of them already converge to like binary images.
Oh, I see.
So.
They're already converted. But you said across all your data sets you had 40 individuals?
So yeah, 40 authentic. So 40 people signed their names, and then they have other people to try to forge the names. Yeah.
Question on the pre-training, the retraining of the pre-training thing. You said you allowed the last few convolutional layers to train and the fully connected layers. How did you make that choice?
Oh, it's actually basically, we treat this as a hyperparameter search, so we just adjusted the trainable. So we tried to not train the CNN layers, and then it works not as well as training the last 3 layers of CNN.
Did you try to train them all?
No, we didn't.
And did you use, when you trained the CNN layers, you were using the same learning rate across everything? Okay.
It's adaptive learning rate. It was adaptive learning rate.
Okay.
But we started with the.
Yeah.
But it was everything was learning with the same learning rate. It wasn't like one thing that people do talk about is lower learning rates on the pre-trained convolutional layers.
No, I did not do that.
And then finally, for your hand-collected data set, great that you did that. It's very important to learn that, I think. It's maybe one of the more important things to learn here. How many signatures were in the final data set, the one that you made?
So
how many people? Sorry.
So how many? So we have collected more than 10 copies of the handouts that we handed out in the common room, and then So
10 people.
No. So there were people. So there were many celebrity signatures on that handout, and some people tried only filled out some of them. So it's not really a balance.
So you asked people to forge pre-existing signatures.
Yes.
Okay.
And then the testing accuracy on that testing set is not really good. So we try to find more data sets online to do the testing instead of using our own self-collected data sets.
But that's what you were reporting on at the end.
No. So the slides were kind of because it was made on that Tuesday night. I mean, this slide is we didn't have that number over there because we didn't really do testings on the. We did testing on the self-collected data set, but then the results were not good. So we were kind of wondering what went wrong. So we tried to go.
The number you reported was on the self-collected data set or something else?
Something else. So some other data set we found
Okay.
online.
I didn't hear you say that when you presented. It's important to
Okay.
correct slides. I get that this is a week later. Okay. Mike?
You cut up the signatures, right? So my first question is, are those random cuts? Because it doesn't look like you cut it right in the center. Are you just randomly
No,
choosing an
so
X and
we-
Y coordinate to cut at? Or?
We cut them so that each cut pieces have the same number of like white pixels, so strokes on them.
Okay. And so you trained on those cuts, and all of those testing validation accuracies that looked really high were also
No.
just tests against cuts or tests against full signatures?
Full signatures.
Oh, interesting. And
Yeah.
it still didn't generalize very
Yeah.
well. Okay. Okay, that was my question.
Okay.
Any comments, questions? Thoughts? Everybody's quiet today. Okay, thank you.
Thank you.